It's helpful to know what type of discontinuities arise and be able to classify them for functions. So for example, we have three different types. The first type is what we call a removable discontinuity. The second has a jump discontinuity, and the last is an infinite discontinuity. So let's examine each of these graphs individually and find out which part of the definition of continuity that is violated. So in this case, we can see that the limit as x approaches a of f of x does exist. I can push this direction and that direction, and we will come up with a single value. The left and right hand limits do agree. We can also see that f of a is defined, given by this point here. The problem with this in a removable discontinuity is that the limit as x approaches f of x does not equal the function value f of a. In a jump discontinuity, the limit, the full limit as x approaches a of f of x does not exist. But the reasons for it are different. If we look at the right-hand limit, it approaches the value, and the left-hand limit approaches the value. So the left and right limits exist in a jump discontinuity, but they do not agree. But they do approach an actual value, not an infinite value. When we have an infinite discontinuity, what we have then is an infinite limit. So if you evaluate the limit and it doesn't exist for the function, but we can assign either a positive or negative infinity to that. Remember, these limits don't exist. We just assign, we say that they're infinite. Okay. Then you have an infinite discontinuity. So it's easy to see discontinuities once you have the graph. It's a little bit harder to determine discontinuity if you have a function. So let's examine that. Okay. So for our first function, f of x, we can see that the domain is that x cannot equal 2. So let's examine the limit and what happens. Remember that rational functions will be continuous on their entire domain. So let's see what's happening to that limit so we can classify the discontinuity there. So we need the limit as x approaches 2 of f of x. And if we directly substitute in 2, we'll get 2 squared is 4 minus 4 is 0, and 2 minus 2 is 0. And this is not helpful for us. So let's look a little bit further. Could we manipulate this function? Well, we could say that f of x, I could factor this into x minus 2, x plus 2, and then just copying the denominator. We can see that when I write it this way, there's a common factor of x minus 2 that can be canceled. And when we do that, we have the limit as x approaches 2 of just simply x plus 2. And now by direct substitution, we see that this is equal to 4. So this limit exists. The function value does not exist, f of 2, but the limit, the full limit, does exist. So we can say that this is a removable discontinuity. Now with g of x, again, if we can see with the domain here is x cannot equal negative 1. So this is a rational function. Let's examine what happens when you take the limit as x approaches negative 1 of g of x. Well, by direct substitution, -1 plus 2 is 1, and -1 plus 1 is 0. And this is undefined. And there's no way that we can manipulate this function like we did for f to remove that. So this is an infinite discontinuity. In h of x, what we have is a piecewise function. The piecewise functions are made up of polynomials. We know that these are continuous for every value in their domain, and that the domain is all real numbers. Now, each branch is determined, though, by their separate domains. And the breaking point of their domains happens at x equals 3. So we need to determine what is happening at x equals to 3. So let's see if h of 3 is defined. Of course it is. X equals to 3 is in the first branch, so we could just evaluate this. And -9 plus 4 is equal to -5. So h of 3 does exist. But now we should look at, then, does the limit of this function as x approaches 3 exist? So let's look at that. So we want to look at the limit. Now I have two different branches, so I have to examine it on both ends. So we'll look at what happens as x approaches 3 from the left-hand side of h of x, which is equal to the limit as x approaches 3 from the left-hand side. And we pick the appropriate branch. The left-hand side are the values where x is less than 3, so we need to evaluate the limit of -x squared plus 4. And when we put this in by direct substitution, we see that this is -5. So the limit as x approaches approaches 3 from the left is -5. Now let's examine the right-hand limit. So we take the limit as x goes to 3 from the right of h of x. And again, we'll pick the appropriate branch. If we're on the right-hand side of 3, the values of x must be greater than 3. So that's the same thing as looking at the limit as x approaches 3 from the right of 4x minus 8. And by direct substitution, we get 12 minus 8, which is 4. And here we can see the problem then. -5 does not equal +4. So the left and right hand limits do not agree here, and h of 3 is defined, and this is an example of a jump discontinuity.